In the sterile corridors of the Laser Interferometer Gravitational Wave Observatory in Louisiana, Dr. Amara Singh stares at a signal that should not exist. The gravitational wave detector has just recorded the merger of two black holes, but the data contains an anomaly that defies every model of general relativity. Instead of the clean chirp pattern expected from colliding black holes, the signal carries embedded frequencies that seem to encode information, vast amounts of it, far more than should be possible given the system's apparent mass and energy. As she runs the data through increasingly sophisticated analysis algorithms, a disturbing possibility emerges. These black holes aren't just warping spacetime around them, they're warping time itself, creating closed loops where information from the future somehow influences the past. The implications are staggering. If black holes can indeed manipulate the flow of time, then every one of these cosmic monsters might be a repository of information from across the entire history of the universe, including events that haven't happened yet. This extraordinary possibility forces us to confront one of the most radical questions in cosmology. Are black holes simply gravitational prisons from which nothing can escape? Or are they actually sophisticated time machines that preserve and manipulate information across all of cosmic history? To understand this temporal mystery, we must journey back to the theoretical foundations of black hole physics, where the work of brilliant minds like Stephen Hawking, Roger Penrose, and Jacob B. Kenstein revealed that these objects are far stranger than anyone had initially imagined. When a massive star collapses under its own gravity, creating a region where spacetime curvature becomes so extreme that not even light can escape, something remarkable happens to the nature of time itself. According to Einstein's general theory of relativity, time is not the universal constant that our everyday experience suggests. Instead, it flows differently depending on the strength of gravitational fields and the relative motion of observers. Near a black hole, where gravity reaches its most extreme values, these time dilation effects become so pronounced that they fundamentally alter the relationship between past, present, and future. From the perspective of a distant observer watching matter fall into a black hole, something extraordinary occurs. As the infalling material approaches the event horizon, that invisible boundary beyond which escape becomes impossible, it appears to slow down and freeze, its image becoming increasingly redshifted until it fades from view. But this isn't just an optical illusion. According to the mathematics of general relativity, the information contained in that matter becomes permanently imprinted on the black hole's event horizon, where it remains for the entire lifetime of the black hole. This phenomenon, known as the holographic principle, suggests that black holes are essentially two-dimensional information storage, devices masquerading as three-dimensional objects. Every piece of matter that has ever fallen into a black hole throughout cosmic history, every star, every planet, every grain of dust, has its information encoded on the event horizon's surface. The black hole becomes a kind of cosmic library, preserving perfect records of everything it has ever consumed. But the story becomes even more extraordinary when we consider Hawking radiation, the quantum mechanical process by which black holes slowly evaporate over vast periods of time. Stephen Hawking's groundbreaking 1974 calculation showed that black holes emit thermal radiation due to quantum fluctuations near the event horizon. Virtual particle pairs that constantly pop into existence throughout space occasionally have one member fall into the black hole while the other escapes as real radiation. This process presents what became known as the information paradox. If a black hole can completely evaporate through Hawking radiation, what happens to all the information that was encoded on its event horizon? Quantum mechanics insists that information cannot be destroyed. Yet the thermal nature of Hawking radiation seems to suggest that all the complex information that fell into the black hole is lost forever, replaced by random thermal photons. Recent breakthroughs in theoretical physics suggest a radical solution to this paradox, one that transforms black holes from information destroyers into information time machines. The work of researchers like Leonard Susskind, Juan Maldacena, and others has revealed that the information falling into a black hole doesn't simply sit passively on the event horizon. Instead, it becomes entangled with the Hawking radiation in ways that create what physicists call wormhole connections, or Einstein-Rosen bridges. These quantum wormholes don't permit faster-than-light travel in the science fiction sense, but they do create unexpected connections between different regions of spacetime. Information that falls into a black hole today might become entangled with Hawking radiation that won't be emitted for billions of years in the future. In effect, the black hole creates causal connections between different epochs in cosmic history, allowing information to flow backward in time through quantum channels that exist entirely outside our normal spacetime. The European Southern Observatory's Event Horizon Telescope has provided the first direct images of black hole event horizons, revealing the glowing accretion disks that surround these invisible monsters. But these images might represent only the visible surface of far more complex temporal structures. If black holes are indeed quantum time machines, then the light we observe from their accretion disks might carry encoded information from across cosmic history, messages from the past and future that we simply don't yet know how to decode. Dr. Singh's gravitational wave detection might represent the first observational evidence of these temporal effects. When two black holes merge, they don't just combine their masses and angular momenta. They merge their entire information content, creating a brief moment when the quantum entanglements that connect different epochs in cosmic history become accessible to external observation. The complex frequencies embedded in the gravitational wave signal might be the universe's way of revealing its hidden temporal architecture. Computer simulations of black hole mergers run on the world's most powerful supercomputers are beginning to reveal the extraordinary complexity of these events. The numerical relativity codes that model colliding black holes must solve Einstein's field equations in their full nonlinear glory, tracking how spacetime itself warps and writhes during the merger process. Recent simulations suggest that these events create temporary time bridges, regions where the normal flow of causality is disrupted and information from different epochs can interact. But the implications extend far beyond individual black hole mergers. If every black hole in the universe is a repository of temporal information, then the cosmos contains a vast network of interconnected archives that preserve records of cosmic history spanning billions of years. The supermassive black holes at the centers of galaxies, some containing the mass of billions of suns, would represent the ultimate historical databases, quantum libraries that have been collecting information since the first stars formed. The Milky Way's central black hole, Sagittarius A, has been consuming matter for over 10 billion years. If the time machine hypothesis is correct, then this 4 million solar mass monster contains encoded information about every significant event in our galaxy's history. The formation of the first stars, the chemical enrichment of the interstellar medium, the births and deaths of countless stellar systems, and perhaps even records of ancient civilizations that might have existed billions of years ago. Advanced civilizations, if they exist, might have discovered ways to access this temporal information archive. Instead of building conventional time machines that require exotic matter and impossible energies, they might have learned to decode the quantum information stored in black holes, gaining access to perfect records of cosmic history. In this scenario, every sufficiently advanced species would eventually become cosmic historians, capable of observing any event that ever occurred within their galaxy's gravitational influence. The James Webb Space Telescope's observations of the most distant galaxies provide tantalizing hints that this temporal information network might already be influencing cosmic evolution in subtle ways. Some of the earliest galaxies observed by JWST appear to contain supermassive black holes that are far larger than current formation theories can explain. If these black holes are accessing information from future epochs through quantum entanglement, they might be growing according to patterns that won't be fully understood until much later in cosmic history. This temporal information flow might also explain some of the fine-tuning problems that puzzle cosmologists. The fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light appear to be precisely calibrated to allow the formation of complex structures like stars, planets, and life. If black holes can access information from the future, They might be influencing the early universe in ways that ensure the emergence of the very civilizations that will eventually decode their temporal archives. The anthropic principle takes on new meaning in this context. Rather than requiring an infinite multiverse to explain why our universe appears fine-tuned for complexity, the black hole time machine hypothesis suggests that the universe might be engaged in a kind of temporal bootstrap paradox, influencing its own initial conditions through quantum information flow from future to past. Quantum entanglement experiments on Earth are beginning to reveal the strange temporal properties that might operate on cosmic scales within black holes. Recent demonstrations of retrocausality in quantum systems show that quantum measurements can sometimes appear to influence the past states of entangled particles. If this effect operates within the extreme gravitational fields of black holes, it might create stable causal loops where information becomes temporally self-consistent across cosmic history. The Large Hadron Collider's high-energy particle collisions occasionally produce microscopic black holes that exist for less than 10⁻23 seconds before evaporating through Hawking radiation. These tiny objects might be creating miniature time bridges, allowing information from particle collisions to influence previous experimental runs through quantum entanglement effects. The statistical patterns observed in particle physics experiments might actually contain encoded information from future collisions, creating a temporal feedback loop that influences the fundamental constants measured in laboratory settings. String theory, that ambitious attempt to unify quantum mechanics and general relativity, provides mathematical frameworks that make black hole time machines not just possible, but inevitable. In higher dimensional spacetimes predicted by string theory, black holes become far more complex objects with internal structures that can support stable time-like loops. These structures might allow information to flow backward in time while still preserving the causal consistency of spacetime on large scales. The holographic principle, emerging from string theory and quantum gravity research, suggests that all the information in any volume of space can be encoded on its two-dimensional boundary. If this principle applies to the universe as a whole, then all of cosmic history might be encoded on the boundary of our observable cosmic horizon. Black holes, as the most extreme manifestations of spacetime curvature, might serve as access points to this cosmic holographic information, allowing advanced civilizations to read the universe's complete history from any sufficiently massive gravitational archive. But accessing this temporal information would require technologies and theoretical understanding far beyond our current capabilities. Decoding the quantum information stored in black holes would involve manipulating quantum entanglement on cosmological scales, requiring precise control over gravitational fields and quantum states that operate at the Planck scale, the smallest meaningful unit of spacetime structure. The search for extraterrestrial intelligence takes on new dimensions when viewed through this temporal lens. Advanced civilizations might communicate not through radio signals or laser pulses, but through carefully orchestrated manipulations of black hole information content. By dropping precisely encoded matter into black holes, they could send messages backward in time to earlier epochs, creating a kind of temporal internet that spans cosmic history. These temporal communications might already be embedded in the cosmic microwave background radiation, that ancient afterglow of the Big Bang that fills all of space. If advanced civilizations from the far future have learned to manipulate black hole information content, they might be encoding messages in the quantum fluctuations that eventually become the temperature variations we observe in the cosmic background. Every measurement of cosmic microwave background anisotropies might be revealing communications from civilizations that won't exist for billions of years. The implications for the future of human civilization are profound. If we can eventually learn to access the temporal information stored in black holes, we might gain the ability to observe any event in cosmic history with perfect clarity. The formation of the solar system, the origin of life on Earth, the rise and fall of previous technological civilizations. All of this information might be preserved in quantum archives that surround us throughout the cosmos. But this capability would come with enormous ethical responsibilities. The ability to observe the past with perfect clarity would eliminate privacy across all of history. Every thought, every action, every moment of every sentient being who has ever lived might be accessible to future civilizations with sufficient technological sophistication. The universe might be far more transparent and interconnected than we ever imagined. The paradoxes multiply when we consider the possibility of influencing the past through black hole information manipulation. If information can flow backward in time through quantum entanglement channels, then sufficiently advanced civilizations might be able to alter historical events by carefully controlling what information falls into black holes in their epoch. The past might not be fixed and immutable, but rather an ongoing collaborative project between past and future civilizations working together across the temporal information network. Standing in that Louisiana laboratory, analyzing gravitational wave signals that might contain messages from across cosmic history, Dr. Singh realizes she might be decoding the universe's first transmitted temporal archive. The merger she observed might have created a brief window where information from billions of years of black hole accumulation became accessible to external observation. The complex frequency patterns in the signal might be the cosmic equivalent of archaeological artifacts, evidence of events and civilizations from across the galaxy's history. But accessing this information requires developing entirely new theoretical frameworks and observational techniques. Current gravitational wave detectors can barely measure the gross properties of black hole mergers, their masses, spins, and orbital characteristics. Extracting the temporal information that might be encoded in these signals would require sensitivity improvements of many orders of magnitude, along with theoretical breakthroughs in our understanding of quantum gravity and the nature of time itself. The next generation of gravitational wave observatories, including space-based detectors like the Laser Interferometer Space Antenna, might provide the sensitivity needed to detect temporal information signals. These instruments will be capable of observing gravitational waves across a much broader frequency range, potentially revealing the complex information structures that current Earth-based detectors cannot resolve. Advanced artificial intelligence systems might also play a crucial role in decoding temporal information archives. The patterns embedded in gravitational wave signals from black hole mergers might be far too complex for human analysis, requiring machine learning algorithms that can identify subtle correlations across vast amounts of data. These AI systems might eventually learn to read the universe's temporal archives like cosmic historians, extracting information about events that occurred billions of years ago or haven't happened yet. The philosophical implications are staggering. If black holes are indeed cosmic time machines that preserve perfect records of all events across cosmic history, then the universe becomes a kind of eternal library where nothing is ever truly lost. Every moment of beauty, every act of love, every flash of creativity that has ever occurred becomes part of a permanent cosmic record that transcends individual mortality and even species extinction. This perspective transforms our understanding of meaning and purpose in cosmic evolution. Rather than brief, isolated flickers of consciousness in an indifferent universe, we become participants in an ongoing cosmic story where every action contributes to a permanent historical record that spans all of spacetime. The universe becomes not just a collection of matter and energy, but a vast information processing system where the past, present, and future are intimately connected through quantum entanglement networks centered around gravitational singularities. The search for a theory of quantum gravity takes on new urgency in this context. Understanding how information flows through black hole time machines might provide the key insights needed to unify general relativity and quantum mechanics, the holy grail of theoretical physics. Such a unified theory would reveal the deepest principles governing the universe's temporal information architecture, potentially allowing us to decode the cosmic archives that surround us. As we stand at the threshold of this temporal revolution in our understanding of black holes, we face questions that would have seemed like pure fantasy just decades ago. Are we living in a universe where the past and future are constantly communicating through quantum channels? Do black holes preserve perfect records of cosmic history, including events that haven't happened yet? Are we on the verge of discovering that time itself is far more malleable and interconnected than we ever imagined? The answers to these questions might transform not just our understanding of cosmic evolution, but our entire conception of what it means to exist as conscious observers in a universe that might be far more aware of itself than we ever dared to hope. In our quest to understand black holes, we might be discovering that the cosmos itself is a vast, temporal, information processing system, where every moment contributes to an eternal story that transcends the boundaries of space and time.